Hello again, everybody, and welcome back. We're continuing our Chapter 10 notes on momentum, and we're going to pick up with what we'll probably call Section 2 right here on a concept called impulse. Now, to kind of understand this, we need to sort of back up a little bit and kind of recap what we talked about in terms of the definition of momentum. So I'm going to come back to the slide in just a second. But let's sort of review what momentum is and how it kind of relates to force, because impulse is something that relates force to momentum. All right, so let's back up just a second. So as we talked about in the first section, our momentum, P, equals mass times velocity. All right, and that's a vector. Velocity is a vector. Okay, well, we also know from Newton's second law that the net force on something equals mass times acceleration, right? You guys recall that? So let's take that acceleration and break it down. Net force equals mass times, what really is acceleration? Acceleration is nothing more than a change in velocity over a change in time. You agree? All right, so we can say net force is equal to that. All right, well, look at this right here. I'll change to a different color. mv and mv, the only difference right here is that the velocity is changing. Well, you can have a changing momentum as well. So what we can really say is that the net force on something is a changing momentum over change in time. That is what that is telling us. All right, so our net force on an object equals some sort of change in momentum over some sort of change in time. And we actually stated that in one of our previous slides. Let me back up even further just a second. There it is right there. Okay, net force is a change in momentum over a change in time. Well, this right here, this principle, this idea is what is going to be what lays the groundwork for this idea of impulse. All right, well, impulse. Our definition of impulse is simply the average force, or you might say the net force, times the amount of time that force acts on it. Okay, so impulse is force times time. So if you apply a force for a greater amount of time, you have a greater impulse. Or if you apply a greater force for a certain amount of time, you have a greater impulse. Okay. But since we just talked about the fact that force and time are linked to each other through what? Let's back up again. Through momentum, right? Through a change in momentum. We can take this equation right here and rewrite it. So we can say that the net force, or the net average force, multiply up that time right there, times a change in time, equals our change in momentum. And that's what that tells us right below, right here. The impulse is simply nothing more than a change in momentum. All right, that I right there. It is a vector. It is a vector quantity. It has a direction, because a change in momentum has a direction, because momentum is a vector quantity as well. So for a given change in momentum, it can either take place by applying a greater force over a smaller amount of time, all right, or it can be over from applying a lesser force over a greater amount of time. And before we go on, I just want to sort of illustrate this. Well, actually, let me show you the next slide real quick, and then I'll do sort of a thought experiment before we do our first example, okay? So a baseball is a great example of momentum change, okay? You've got a ball coming in right here. It's coming in from the pitcher with some sort of velocity, and then it leaves the bat, assuming it's a good batter, with a different velocity, probably a greater velocity, because the bat is imparting some sort of force to it. All right, but does the ball get stuck to the bat for very long? Well, in this picture, it seems like it is, but it's really just a very high-speed picture. That bat and ball, I guess it looks like a softball, not really a baseball, but they're in contact for a very short period of time. So this force, that force right there, is applied for a very short period of time. So remember what I said before about the relationship between force and time. There has to be a very great amount of time and a very small force, or a very great force or in a very small amount of time. And of course we know from baseball that the ball and the bat are not connected for a very long period of time. So it must be a really great force. That's a greater sign right there, all right? So it's a very small amount of time. But it results in a change of momentum. That ball is coming in at some sort of, we'll say it's got a negative momentum, negative direction, all right? And it leaves the bat in with a positive momentum. So is the force constant? Well, no. As the ball kind of contacts the bat, you can see there's more and more and more force on it, and then as it leaves the bat, the force gets less and less and less. But if we were to take that and average it out, that would be the average force that we would put in here to find the change in momentum of this ball. All right, so the force is not a constant force, but we can find an average, and we're going to pretend that they're average forces going forward in the problems that we're using. Okay, another way to think about this is like this. I'll go to a blank slide right here. Let's say, there we go. Let's say you are dropping an egg. All right, now we had a problem, I think a few problems back, where we had to calculate how high you could drop an egg from and have it not break. Let's say that it's a pretty high height right here. All right. And I'll change colors here. We have a red egg apparently. Here's the ground right here, and here's the ground right here. All right, well, when the egg hits the ground, or right before the egg hits the ground, so it falls down, and it has some sort of velocity right before it hits the ground, it means it's got some momentum, right? So momentum initial is something, okay? Same here. Momentum initial equals something. All right, what's the final momentum? Momentum final equals 0, right? 0 kilogram meters per second. Momentum final equals 0 kilogram meters per second. All right, what's the difference between these two right here? Well, if you drop this egg straight on to the ground, it's going to break. Why is it going to break? Well, because it takes very little time for it to go from having momentum, initial momentum, to no momentum, right? So the time is great. I'm sorry, all the way around. The time for a given momentum, so going from, so change in momentum here equals the change in momentum here. That is, the egg is going from having momentum to rest, from momentum to rest, okay? Well, that means the time, if it comes to rest very, very quickly right here, the time is small, which means the force, that's a big F right there, the force is very big, all right, to produce that change in momentum, going from moving to not moving. And of course, with a very great force, that means the egg is going to splatter and break. All right, but what if you had, let's say, we'll make this green. What if you had some sort of a mat or a cushion? All right. Well, you still have a change in momentum because this cushion is going to compress. Right. So our egg is going to. Oops, that went back to. Sorry. Our egg is going to come to rest right there, and so our final momentum is 0. But what's different right here? What's different? Well, the amount of time that this egg is coming to rest from, let's say, from right here where it was moving to where it's not moving, to where it has no momentum, time is greater. You've got a greater amount of time that you're applying that force, which means for a given momentum, right there, that means the force is going to be much smaller. Okay, so the momentum change is the same. It's dropping from a height and coming to rest. So if going from some momentum to 0. Dropping from height, coming to rest, going from some momentum to 0. But you can determine how much force is imparted to the egg. If you apply that force, that stopping force, very, very rapidly, that means the time is small, that means the force is going to be huge. If you allow this egg to come to rest over a longer period of time, if time is greater, then for a given momentum change, that means the force is going to be less, which is why if you drop it on the right kind of cushion, that egg will not break because it's not experiencing the force required for it to break. That's the idea right there. Perhaps you've even experienced this when you do like egg tosses. And how do you catch it? You try to catch it and move your hand back so that you catch that egg over a longer period of time. The greater the time, the less the force. The lesser the time, the greater the force. And that's what impulse is right there. All right, so if this ball is contacting the bat for a very short period of time, small time, that means the force on that ball is going to be enormous. And that ball, if it's hit right, is going to go sailing out of the park. So let's do an example on just that topic, changing baseball direction. And that'll be our example 2. And then that'll be it for this segment. Okay, so we have an 0.144 kilogram baseball, which I think is actually the right mass of a baseball. All right, so here's our mass right here. I'll write this up at the top, actually. I don't feel like going to a separate slide. Mass of the ball is 0.144 kilograms. And the initial velocity, in fact, I should, no, that's all right. I'll put the initial velocity over here, and I'll put it in, no, I don't want to change colors. Initial velocity is 43.0 meters per second. All right. Now, we need to, since velocity and momentum are vectors, we need to establish a coordinate system, right? Which direction is negative, which direction is positive. All right, well, I'm going to call this direction positive and this direction negative right here. So if the ball is initially moving in this direction, it's initially moving at negative 43 meters per second. Okay, well, the force that the bat exerts is a lot. It's actually thousands of newtons. 6.5 times 10 to the 3rd newtons. All right, so that's 6,500 newtons, which we divide that by 4. I don't know. That's like 1,500 pounds, I guess. So it's a lot of force. For a time of 1.3 milliseconds. Wow, that's a really short period of time. Time equals 1.3 milliseconds. So that's 1.3 thousandths of a second. So which means to convert it to seconds, we have to move that decimal point over to the left 3 places. So it's 0.0013 seconds. That's going to be our time that this ball is in contact with the bat. All right, that's experiencing this average force of 6.5 times 10 to the 3rd newtons. Okay, so we're going to take, like we said before, okay, it's even mentioned in the problem right here, towards the pitcher is going to be the positive x direction. So it's initially coming in negative and it's going to leave. We do know that the final velocity is going to be positive, but we don't know what. Okay, so let's find the impulse on the ball, and then we're going to find the final speed of the ball. Okay. So I'm going to do that actually over on the, let's see here. In fact, maybe I can just move all this stuff around. There we go. We've got all kinds of extra space here now. Like so. All right, so let's do part A right here. The impulse is what we want to find out. Okay, well, the impulse is nothing more than the change in momentum. All right, and of course, change in anything, this is part A, change in anything is final minus initial, right? So that's momentum final minus momentum initial. So let's find out what that is. Let's find out the impulse on the ball. Actually, wait a second. We can do that even easier. Sorry. We could have done this before, find our final momentum and find our initial momentum. and then subtract them to find the impulse, but let's not do that. I'm getting ahead of myself right here. What is our working equation for impulse? And it right here, right? It's simply force applied over time. And we do have force and we do have time. So let's go back and finish solving. While this is true, impulse, like we just said, is simply force times time. And just multiply them together. All right, so that's 6.5 times 10 to the third newtons times how many seconds? That's 0.0013 seconds, and that's going to be our impulse, which really is our change in momentum, which may just come in handy a little bit later as well. But what is that? So 6.5 times 10 to the third times 0.0013, I get 8.45. What? Well, it's change in momentum, so it's going to be the same units as momentum. Kilogram meters per second. That's going to be our impulse, also known as the change in momentum. Okay? So, if we're finding the final speed of the ball, oh, that's actually kind of funny. We would not have been able to solve using this anyway because we don't know the final momentum, right? Because we don't know the final speed or the final velocity, but we will be able to right now. And here's why. Because if impulse equals a change in momentum, then that means 8.45 kilogram meters per second equals momentum final minus momentum initial. Okay, so let's solve and find this final momentum. If we find that, we can find the final velocity. Make sense? Okay, so this is part B right here. Momentum final minus momentum initial equals 8.45 kilogram meters per second. All right, let's solve for our final momentum. Now, actually, you know what? We don't even want to do. We want to solve for the final velocity, right? So, mass times velocity final minus mass times velocity initial, right? Isn't that our definition of momentum? Equals 8.45 kilogram meters per second. All right? This is what we're solving for. I was trying to get ahead of myself and trying to plug in values before writing a general equation. Let's write our general equation first, and then we'll solve for it. So what are we going to do? I'm going to add, add this MV initial over to that side, and then I'm going to divide everything by that mass of the ball. Okay? So I'm going to come over to, no, I'll just do it right here. V final equals 8.45 kilogram meters per second. That's a change in momentum. Plus mv initial, right? That's our initial momentum. All that divided by the mass. Now we can plug in, because we have a general equation solving for that final velocity right there. All right, so v final equals 8.45 kilogram meters per second plus, hope I have enough room here, the mass is 0.144. I'm going to leave my units out, sorry, just because of space here, times what's our initial velocity. Our initial velocity is a negative velocity, right? So it's negative 43.0 meters per second. All right, fit those units in, but not kilograms. This is kilograms right there, okay? All that divided by, I'll put the kilograms down here, 0.144. There's our kg, because I had some more space. Now we should be able to solve for the final velocity, okay? Let's plug everything in and see what we get. 0.144 times negative 43 meters per second, and keep an eye on your signs right here. Signs are going to be very, very important, all right? So that's 8.45. I did my multiplication first. All that divided by 0.144. And I get an answer of 15. Oops, I'm trying to write with my laser pointer again. 15.7 meters per second, which is actually moving pretty fast. Okay? So let's recap what we did right here. We defined impulse as being our change in momentum. We actually could not have done this right here, even though I tried to write it down initially. Why? Because we did not know the we did not know the final momentum at the outset. We had to actually solve for that, all right? But we did know that the change in momentum or impulse is force times time. We had our force, we had our time, and we solved for the impulse, which is also known as the change in momentum right there. Then we said, all right, well, to solve for the final velocity, we need to know the final momentum. And then we could say, all right, the final momentum minus the initial is that change in momentum. Plug in our mv final, mv initial, all right, and solve for our final velocity right there. That's what we just did right over here. We got our 15.7 meters per second. And of course, it makes sense that it should be positive because it's moving outwards in the positive x direction, right, towards the pitcher or towards the outfield. All right, so that's our little kind of foray into impulse and change in momentum, which are the same thing. We're going to have some other videos in the future dealing with more examples of this, but this will take us pretty far into section 2, so I hope you understood that. If you didn't, please make sure you see me, but in the meantime, thanks for following along, and I'll see you on the next one.